The span and scope of our Earth's history reveals a process so vast, it has been called deep time. Our Earth systems display a stunning array of complex processes that are all intertwined, including large and small-scale phenomena. We will examine how geologists understand crystal structure at the atomic scale, and how this understanding explains larger processes within the Earth's interior. Our visualization tool will be waves. Waves help us to visualize mineral structures at the microscopic level through the interaction of light with crystals. Geologists use the petrographic microscope to do this microscale investigation. Air and water are isotropic. They have equal physical properties along all axes. An anisotropic material, in contrast, is a material with different physical properties when measured along its axes. A cube of Jell-O is isotropic because its interior is uniform in all directions. On the other hand, Jell-O that is layered is anisotropic because it has strong and weak layers. We are going to use light waves to visualize a mineral's internal structure. When light passes from air to water, the waves are bent or refracted, depending on the indices of refraction in the air and water. Light is refracted when it passes from one substance to another, and refraction is the result of a change in the velocity of the light wave. Birefringence is the splitting of a single ray of light into two rays when it travels through an anisotropic material. Birefringence is a diagnostic property. The mineral olivine has high birefringence, so its mineral grains display brilliant colors, while quartz produces first-order grays because it has low birefringence. Optical birefringence refers to the splitting of light waves, and as we will explore further on, seismic birefringence refers to the splitting of seismic waves. To help you visualize this phenomenon, let's do a simple experiment with the mineral calcite. Calcite has an extremely high birefringence. Draw a line on a piece of paper. When a calcite mineral is placed on top, you can see two lines instead of one. This is because as the light ray, the drawn line, enters calcite, the single ray is split into two. Light entering this anisotropic calcite mineral is split into two rays with different velocities. Two rays vibrate at right angles to each other. When a polarized piece of film is placed on top, we can filter which rays pass through. If the polarized film is rotated 90 degrees, we see only one of the two rays at a time. The sun, a light bulb, and a microscope's light source are all similar in that they all emit white light. White light is made of different wavelengths, and therefore different colors of light. A polarizer is an optical filter that passes and blocks certain waves of light. Some common polarizers are sunglasses and camera lenses. The petrographic microscope has two polarizers. As you turn on the light source of the petrographic microscope, white light travels to your eye. The lower polarizer absorbs all light not vibrating in one plane, typically the east to west, left to right plane. Only the component of light vibrating in the east to west direction can pass through the lower polarizer. This is called plane polarized light. The upper polarizer, which is called the analyzer, typically has planes running north to south, back to front. When you insert the upper polarizer, no light is able to reach your eyes. You see black, which is called crossed polarized light. A thin section is a piece of rock sliced so thin that it is translucent. Crystals on a thin section can reorient light rays. As we slide a thin section under the microscope's lens, we can view the rock's tiny mineral grains. Anisotropic minerals split the plane polarized light into two new components. These rays vibrate perpendicular to each other with different velocities. Of the two components created, one is a fast ray and the other is a slow ray. The difference between the two rays is called retardation. The amount of retardation is determined by the mineral birefringence and the thickness of the thin section. Geologists can make a lot of educated guesses about what happens underneath us through the study of waves and how they travel through the different materials of the Earth. Now let's focus in on the interaction of seismic waves with the Earth's internal layers, a phenomenon of macro proportions. Light rays and seismic waves behave the same way when they travel through an anisotropic media. And it is through this wave behavior that we can come to conclusions about unknown bodies of rock and their crystal alignment. S-waves, or shear waves, are one of two main types of seismic waves, vibrations produced by earthquakes. The waves travel through the Earth's interior and can be measured at the Earth's surface with sensitive detectors. When a polarized shear wave enters an anisotropic media in the Earth, it is split into two shear waves that travel through the Earth. The two waves arrive at seismic stations at different times. The fast ray will reach a seismic station first, and then quickly soon after, the slow wave will arrive. The difference between their arrival times tells us about the anisotropy of the medium it traveled through, just like the amount of retardation in a mineral grain. Seismic anisotropy tells us about the flow in the asthenosphere, as well as the properties of the crust, upper mantle, transition zone, the core, and an area in the lower mantle called D double prime. Data gathered from seismic birefringence helps us understand the Earth's interior and structure, and has confirmed many predictions of mantle flow from plate tectonics theory. The analogous relationship between optical birefringence and seismic birefringence reveals more about the interrelated geologic processes happening on our planet.